So the whole idea of light acting as a particle came about because of a problem scientists were having with what's called the photoelectric effect. The photoelectric effect is where you take a piece of metal and if you shine an intense enough light on it, you can get electrons to be ejected from the surface of this metal. And the idea at the time, the classical theory, said that it should be the intensity of the light, not the frequency of the light, that should determine the energy of the ejected photons. And the classical theory held up for a certain while, so as they increased the intensity of light that they are shining on a piece of metal, the electrons coming off would be more and more energetic. But there came a point where this would stop, that they could not get the electrons to become any more energetic coming off of the piece of metal. And this was a real problem because the classical theory said that, as you increase the intensity, the energy of the electrons coming off the metal should continue to increase. And this represented a problem that needed to be solved. And so it was actually Albert Einstein that came up with the theory that explained what was going on with the photoelectric effect. And this is where Einstein actually received a Nobel Prize for his work in this area. So Einstein is mainly known for his theories on relativity, but it was actually his work on the photoelectric effect that got him the Nobel Prize. And what he said was what determines the energy of the electrons coming off the metal was actually more due to the frequency of the incoming light and less to do with the intensity of the light. So part of Einstein's solution to the photoelectric effect is he proposed that electromagnetic radiation acts like a particle, and he called these particles photons. And they have a characteristic energy to them. So light is broken up into small particles, and each particle is literally just a bundle of energy. And so this idea at the time was revolutionary, and it was by thinking like this that he was able to explain what was going on with the photoelectric effect. So he said light is broken up into these particles or bundles of energy called photons, and then he said that the energy of this photon must equal or exceed a threshold value for the metal called Ework, or the work function, for an electron to be ejected from the metal. So this the metal has this kind of barrier called a work function, and it's the energy of the photon must equal or exceed this value in order for an electron to be ejected. And so this idea follows this equation. So h nu is the energy of the incoming photon. Ework is the work function, which is a property of the metal, and the E sub k is the energy of the ejected electron. So you can see by this is if the energy of the photon is actually less than the work function of the metal, no electron would be emitted. So there would be no E sub k here. That would be 0 or less than 0. So no electron would be emitted. So what you're able to do is, if you understand the work function of a metal, you can find the threshold frequency. You can find the frequency of light at which electrons start to be emitted from a metal. So that's when the frequency of the light would, or this equation would equal Ework. So if we want to find the threshold frequency, we just set h nu equal to Ework like this, and then you solve for the frequency at which the incoming energy of the photons actually start to overcome the work function. So we use this equation here, and we solve for nu, and that's going to be nu naught, which is the threshold frequency. So this tells us if our incoming light has a frequency greater than that, well, then electrons are going to start getting knocked off our metal. So let's do an example of a classic problem involving the work function. So I have a metal, and I know what its work function is, so it's given here. And the metal is struck by a photon of red light. So we know that red light has a wavelength of 680 nanometers. Two things I want to do is say, what is the threshold frequency of the metal? I want to understand, is the photon of red light powerful enough to cause an electron to be ejected from the metal? And if so, what is the kinetic energy of that photon that's being ejected? So remember, the threshold frequency is dependent on the metal, so it doesn't actually need light to be shined on it to calculate that. So threshold frequency is directly proportional to the work function. So here, if I want to find the threshold frequency, I take the work function and divide by h here, and that's going to give me the frequency at which light needs to be in order for an electron to be popped off. So I take the work function, which was given, h, Planck's constant, is a constant, and from that I'm able to calculate the work function of a metal. So that's independent of anything. It's a constant for the metal itself. But once I find this threshold frequency, I'm able to predict is a incoming photon energetic enough to be able to cause an electron to be ejected from this metal. Another way of understanding if an electron is going to be emitted if a photon of light strikes our metal is to just go ahead and find out what the energy of the photon is and compare that energy to the actual wave function. So I told you that a photon of red light is coming in. We know the wavelength of that light, and what I'm going to do here is actually find the energy of that photon. So we know that the energy of the photon is these two constants, Planck's constant times the speed of light divided by the wavelength of the incoming light in meters. So remember, I need to discuss the wavelength of light in meters because our two constants here, h and c, have meters inside of there, are used by them. So the way I like to do it is I just take the wavelength of light and just multiply by 10 to the minus 9. So 680 nanometers is equal to 680 times 10 to the minus 9 meters. So I go ahead and use that. So I calculate what the energy of the photon is. So Planck's constant, speed of light, I can use the wavelength of the light that's coming in, I convert it to meters, and then I come up with the energy of the photon. And what I can do is compare that energy of the photon to the work function. And I can say, is the energy of this photon less than, equal to, or more than the work function? So here the energy of my photon is actually greater than the work function of the metal, and so that tells me that an electron is going to be emitted. So now that we understand that the energy of the incoming photon is actually greater than the work function, we understand that an electron is going to be emitted, and kind of the last step here is we can actually calculate the kinetic energy of the emitted electron. So here we have the energy of the photon that we calculated up here, so we understand that. The work function actually acts as kind of a dampener, so it's going to hold back some energy, so we subtract from that. So we take the energy of the photon, we subtract the work function, and the energy that's left over is going to go into our emitted electron. So previously we calculated the energy of the photon. We then subtract from that the work function, which is a constant, and what's left over is the kinetic energy of the electron.